Chem 106, Chapter 18, Chemical Thermodynamics, Lecture 2. In Lecture 1, we talked about entropy. In this this lecture, we're going to focus on the Gibbs free energy. Gibbs is a scientist who worked out the idea about free energy, which means the energy that's available to do work. It's not literally free. It's energy that's available to do work. And so the equation that he worked out was the enthalpy minus the Kelvin temperature times the entropy, so it was named in his honor, given the letter G. But even though every substance possesses free energy, the actual quantity, just like with enthalpy and entropy, really is not known. And so we study them by their changes. So just like with enthalpy and entropy, we use delta G. And so here's the equation that is really usable. So the real Gibbs free energy equation is the change. The change in free energy is equal to the change in enthalpy minus the Kelvin temperature times the change in entropy. If it's under standard conditions, then of course you have these zeros. So what it means then is if you have a standard Gibbs free energy value that is negative, therefore less than 0, if you have a negative, that process is spontaneous in the direction written under standard conditions at that specific Kelvin temperature. It is very specific to that temperature. So if you have a negative value, that process is spontaneous. If you have a value that somehow actually just equaled 0, then it's neither spontaneous nor non-spontaneous because it's at equilibrium. So it's not, going anywhere. It's not spontaneous nor non-spontaneous, and I'll explain that in a minute. But if you have a value that is positive, so if you have a delta G value that's positive, then that is non-spontaneous in the direction written under standard conditions, notice the 0 there, at that specified Kelvin temperature. The free energy at equilibrium, and remember that's a dynamic equilibrium, where there's a mixture of the reactants and products, is always lower than the free energy of the pure reactants and pure products. There's still free energy in the system, but because it's dynamic equilibrium, the free energy is taken up to keep the system in dynamic equilibrium, having a forward reaction equaling a reverse reaction. So there's no free energy to do any other work in the system. And so delta G is 0 because the system is already doing everything it can. All right, so let's go back and investigate this in the lecture problem. These problems are very, very easy to solve. Let's go to the dry erase app here, and we'll go to problem number 3. It says calculate the delta G0 for a reaction at 25 degrees Celsius. Notice that's why the zeros are there. It's under standard conditions. And so our equation, delta G0 equals delta H0 minus T delta S0. We don't even care what the reaction is, honestly, that the hydrogen reacting with fluorine to make hydrogen fluoride. It's irrelevant because all we're doing is mathematical values here. There's nothing to even do with the chemical equation because we're trying to calculate delta G. Delta H0 was given to you as minus 537.22 kilojoules. The T was 25 degrees C, so we can't use that. Need to add 273.15 to it to get 298.15 Kelvin. And the delta S given to us at delta S0 is positive, and that makes a difference because that explicit positive means something here algebraically. 0.7 joules per Kelvin. Now, notice then that this is a difference operation. The units must be identical here. So this is in kilojoules, and this is just in joules per Kelvin. So, times 1 kilojoule per 1,000 joules, or just move the decimal place 3 places to the left, same idea. It becomes 0.0137 kilojoules per Kelvin. All right, now it's going to work algebraically. Okay, and now see again, it didn't even matter that it was hydrogen fluorine or any of that other stuff because this is just a mathematical problem. All right, so delta G 0 equals minus 537.22 kilojoules minus open bracket now because we got two terms to do here, 298.15 Kelvin times 0.0137 kilojoules per Kelvin. And those kelvins cancel, leaving me with just kilojoules. And so now we can do this operation. So it's going to equal minus 537.22 kilojoules. Now this stays minus because this was positive, so it doesn't change it. Had this been a negative value of entropy, that would have modified this into a positive, but it's still minus. And the result of that is 4.084655 kilojoules. So we end up with negative 541.304655 kilojoules. And of course, we always have to round. And so even though our starting this had 3 significant and that had 5, that's not the point here because this is a difference operation. So this number had 2 decimal places. Temperature doesn't matter. So this had 4 decimal places, so our answer must have 2. So make the cut there. That 4 does not modify the 0. So the final answer here, negative 541.30 kilojoules. Okay. So these problems really are just this easy and straightforward. Let's clear that and go back to the lecture outline. There it is. All right. And we already know the meaning here. So, all right. Let's go down here to letter F. The relationship between the standard free energy change for a reaction and the equilibrium constant K is given by this equation, delta G0 equals minus RTLN K. This is something you need to do also. There's a lecture problem for this, so let's solve this problem as well. Oops, you don't want that. There we are. Sorry, there we are. Okay, so this is lecture problem 4. The standard free energy change for a chemical reaction at 298 degrees Celsius is negative 16.77 kilojoules per mole. What is the equilibrium constant for the reaction of this at this temperature? And I provided the R value there as well. So, oops, always forget to change this back to there. All right, so delta G equals minus RT ln K. And now you're not afraid of natural logs. You've already been playing with them. And so what we want to solve for here is that's the relationship given. And that's if we knew the equilibrium value. But in this case, the question is asking you to calculate the equilibrium value. So you have to do the algebra on this to get it to change over. And when you do, you find out that K is going to be equal to E to the minus delta G over RT. This is the appropriate form of the equation solving for K, because we're going to divide both sides by negative RT, and then we have to take the E of both sides to get rid of the ln. And so K equals E to the negative delta G over RT. So to make this a little more straightforward then, let's solve separately the delta G over RT and get a value for that to plug back in here. All right, so we were told that the delta G is negative 16.77 kilojoules per mole. Is that spontaneous or non-spontaneous, the given free energy? Yes, that's spontaneous. All right, and then the R. Now notice, again, this is in kilojoules per mole. The R given was joules per Kelvin mole, right? So again, you must convert that by dividing by 1,000, move the decimal over 3 places, so you end up with 0.008314 kilojoules per mole Kelvin, and now times the temperature given, which was 298. All right, so we see the Kelvin cancels, the moles cancel, and the kilojoules cancel, and that's what we want because in order to do the log, we really want it to be dimensionless. So when we do this, we get an intermediate value, minus 16.77 over 2.477572, which gives us overall minus 6.76872 3573. So e to the minus 6.7687233, no, 3573. That means these are going to cancel out, so that's e to the 6.768723573, and that's going to give us a raw value of 870.2004374. Now remember, this is a K, so there's no units. We got rid of all the units up here, and so e to that value gives us 870.2004374. And so now we got to figure out the last step, always, of significant digits. The only one usable here is the delta G value, and that's 4 significant digits. And so carry throughout, that still means 4 significant digits, right? But when we do this, then we're going to end up with yeah, 4 significant digits. So that puts us here on this, and that means then, because there's 3 decimal places, we need 3 significant digits here. So when we solve this, then now we can't just say 870, because if you cut it there, that 0 is not significant. So what you're going to have to do is put it in scientific notation. So that's going to be 8.702004374 times 10 to the 2. And now you can cut it there, and that 2 doesn't affect the 0. So your final answer is 8.70 times 10 to the 2. And that's your final answer. All right. So cancel that out. Go back to the outline. There we go. Okay. Now, when we talk about this Gibbs free energy now, again, a value less than 0 means it proceeds spontaneously. A value greater than 0 means it's already beyond and is non-spontaneous. And at 0, it is at equilibrium. Okay. And as I said, the free energy is the maximum energy available to do useful work. And free just means available, not free as in cost. Okay. Last concept here, really, then, is calculating and using free energy. We have an equation just like we did for enthalpy and entropy. And this is the equation, the exact same equation that applies to Gibbs free energy. The Gibbs free energy of reaction is equal to the formation free energies of the products minus the sum of the formation free energies for the reactants. But this is now just like enthalpy. All of the elements in their standard states, or compounds even, elements. All the elements in their standard states have a free energy of 0. So you must remember to do that the elements in their standard states have a Gibbs free energy value of 0, just like their enthalpy values are 0. So we can solve a problem with this then. And let's have a look at this then from the lecture problem. So let's switch back over. There we go. And look at lecture problem number 5. And it says calculate the delta G0 for the reaction below at 25 degrees Celsius. And that reaction is 2 SO3, SO2 gas plus O2 gas yields 2 SO3 gas. All right. So again, delta G0 of reaction is going to equal the sum, delta G formation of the products minus the sum of the delta G, formation of the reactants. All right, so plug and chug. So we got a table, and I'll provide a table to you on the exam as well. Open brackets, our product now has 2 moles. Because remember, you got to take that into consideration in the equation. 2 moles, and then we find SO3 in the table, and we see that that has a value of negative 370.4 kilojoules per mole. And that's the only product, so then minus, open bracket, SO2. So 2 mole. And we find SO2 in the table, and that's negative 300.4 kilojoules per mole, plus oxygen is 1 mole times 0 kilojoules per mole, because oxygen is in its standard state at 298 Kelvin, therefore its Gibbs free energy value is 0. And notice the moles cancel out in all of these. And so we end up with then 2 times that 370 gives us negative 0.8 kilojoules minus 600, because this was Oh, I'm sorry. Minus a minus. My apologies. Let me erase this and say this again. Okay. My apologies for that. So minus a minus 600.8 kilojoules from this. And then that minus minus becomes minus 740.8 kilojoules plus 600.8 kilojoules. And that gives us a raw answer now of negative 140. My pen is acting up. My apologies. Point. And now, again, because this is a addition subtraction operation, you must have 1 decimal point also, even though if it is 0, you got to remember to put that in there. Kilojoules. Okay. So, negative 140.0 kilojoules. Even though your calculator is going to just say 140, you have to remember in the end to put the 140.0 kilojoules. Okay. 140.0 kilojoules. And that's how easy that problem is to do. All right, let's go back to the outline just to finish out here. All right. We already did this calculation under standard conditions, and we did this now as well. The last section is, again, just like the very beginning of this outline, all about theoretical material. This is not on the exam. And so, the free energy is a function of temperature, so that the Gibbs free energy of reaction will change as the temperature changes. Consequence of the dependence on temperature is that in certain instances, reactions can be product favored at equilibrium at one temperature and reactant favored at another. That's why I kept emphasizing about the temperature, that those Gibbs values are only good at a specific temperature. But yeah, changing the temperature, you can change it from spontaneous to non-spontaneous. And so those instances arise when the enthalpy and the T delta S terms work in opposite directions. So an example of this is that processes that are entropy favored and enthalpy disfavored, and things that are enthalpy favored and entropy disfavored. Again, if you're going to stay in math, especially if you're going into chemistry or engineering, I really encourage you to play with this equation, the Gibbs free energy equation, delta G equals delta H minus T delta S, and just substitute in like some negative here and some positive, or some positive and some negative, or negative negative, or positive positive, holding the temperature constant, and see what effect it has on delta G. Or under those same situations, now keep increasing the T or keep decreasing the T, and you can see the relationship that happens mathematically to all of this. But remember, the delta S is in joules And this is in kilojoules, so this isn't quite as much. This is a modifier term to this. So keep in mind how all that works, especially, like I said, if you're going into chemistry or engineering, you're really, for your own benefit, going to want to take a little bit of time and play with this equation. Anything I can do to help, let me know. All right, so using the relationship between delta G and K, which we just solved, we already saw how this relationship provides a direct route to determine the free energy change if you already know the equilibrium constant, or if you already know the delta G, we can rearrange to solve for K, which I showed you how to do that. K equals e to the minus delta G over RT. This is all that you need to know about thermodynamics. There are 5 types of problems to work with, and we've worked all 5 types. This concludes Lecture 2.